Here we're going to go over the serial sequence recognizer circuit. This circuit is a sequential circuit that takes a serial input stream of bits and then outputs a single bit, 0 if the sequence that is being checked has not been recognized, and 1 if the sequence has been recognized. The high-level block diagram of this circuit looks like this. We'll have an input I, an output O. We'll have a clock and a reset. Now, if we were to have a serial sequence that we wish to see was 0, 1, 1. This means that if we saw an input sequence of 0, 1, 1, then the output O would output 1. If sequence is seen, output 1, else output 0, right? So let's go through an example sequence. Say we go 1, 1, 1, 1. So the first bit we see, we've only had one bit, so the output is, so this is the input sequence and this is the output sequence. Here we've only had one bit, so the output is 0. Here we've seen 1, 1. This is not the sequence 0, 1, 1, so the output is 0. Then we look at this sequence. 1, 1, 1 is different from the sequence we're interested in, so 0 again. Next we have 1, 1, 1. The output is 0 again. Let's try an input 0. Now we have an input sequence 1, 1, 0, but it's different from our output sequence 0, 1, 1, so we output 0 again. Let's input a 0 again. The input sequence is 1, 0, 0. It's different from what we want, so we output 0. Let's input a 1, 0, 0, 1. It's not what we're interested in, so we output a 0 again. But if we input a 1 on this sequence, on this point, we have 0, 1, 1. It is the same as the input sequence. Finally, we output a 1. On the next clock cycle, say we input either 1 or 0, we're going to get 0. Why? Because if we have 1, 0, 1, 1, 0, it's different from our input sequence that we desire, so it will output a 0. And if it was 1, 1, 1, well, it would still be 0 again. So say we input a 1 now. 1, 0, 1, we output a 0. Say we input a 1 next. 0, 1, 1, and we see that it matches again, so we output a 1 again. And this sequence continues on forever until the system is reset or until it loses power. How do we construct a state diagram that solves this problem? Well, we have an input. Well, let's draw the generalized state block diagram, or the generalized digital circuit for the state machine. So we have combinational logic, and then we have our sequential logic, our register. Let's draw how it's connected here. right? Then the next state bit feeds into the register. Current state comes from the register. So n bit, current state, next state. We also have an output here. Actually, we can label this just O for m bit where m equals 1. And we have an input I, k input where k equals 1 as well. We should now declare the state machine. Well, how many bits are in the sequence? There are 3. But there are 4 general states. Recognized 0 bits. If our first input, notice here on this first column, is a 1, this is the first bit input, then we have recognized 0 bits. 0 bits. So we need to keep track of whether we've recognized 1 bit or no bits. We can say we've recognized 1 bit, the 0. We can say if we've recognized 2 bits, 0 and 1. And we can say if we've recognized 3 bits. So we have 1, 2, 3, 4 states that we can use. Now, it may be possible to optimize the state machine, but this is what we're going to use to get it started. We're not going to focus so much on minimizing the number of states. In any event, we're going to need a minimum of 2 state bits anyway, as we shall see shortly. So, let's say we've recognized 0 bits. We'll call this state 0, 0. That'll be the 0 state. Recognized 1 bit. Recognized 2 bits. And recognizing 3 bits. So on 0, 0, if we get a 0 input, we have recognized 1 bit. Have we recognized the sequence? No, so the output O is 0. If we are on state 1 and our input is 1, that means we are looking at, so let's write the sequence, 0, 1, 1. We've already recognized 1. Here we take in a 1 and we output a 0. When we transition 1, 0 to 1, 1, we input a 1 and we output a 1 because we recognize the state. We recognize on this state that we are completing the sequence. Now, from state 1, 1, we can take in either a 0 or a 1. And we have to decide where to go now. Well, if we take in a 0, where do we go? Well, we can go here. If we take in a 0, we output a 0. Notice that we have recognized here a 0, the first bit. The only place a 0 appears is the first bit, so we have to go back to state 1 when we see a 0. Anytime we see a 0. Right? What about if we see this sequence 0, 1, 1, 1? Well, we haven't recognized any bits. We have a series of 3 1s here. We have not recognized a first bit 0. That's already long past. This one has gone away and is not part of any sequence because the sequence must be size 3. So if we take a 1 as input, we go back to recognizing 0 bits. 1 and output is 0. Now the question, if you're in state 0 and you input a 1, notice you can input 1 any number of times until you enter a 0. You're still going to recognize 0 bits, so you just cycle. Input 1, output 0 as many times as you get clock cycles with a 1 input. So let's take stock of where we are. On state 0, we have an input 1 edge and an input 0 edge. With an input I, 1 bit, that means we need only 2 edges, so we are done with state 0. State 3, we have an output 1 edge and an output 0 edge. Covers all the edges coming out from 3. Now, let's look at state 2. We have 1 output edge here where the input is 1, but what about for input 0? Well, with input 0, we have recognized the first bit again, so we just cycle again. Input 0, output 0. So we recognize if we say 0, 1, 1, this is not much different from saying 0, 0, 1, 1. Instead of recognizing here, we just recognize here. We just keep cycling until we recognize the final 1, 1 sequence. And finally, we have state 1, 0 here. Okay. State 1, 0. If you input a 1, you go to state 3. But what about if you input a 0? Well, you have to go to state 1 again. 0 and output 0 again. And this completes the state diagram. We have 1, 2, 3, 4, 5, 6, 7, 8 edges. Let us draw the truth table for this state diagram. We have an input variable I. How many state bits do we have? We have 2 state bits. N equals 2. Let's call these A and B. We have only one output O, and we have our next state bits A plus and B plus. Implementing the truth table. like so. And now we need to see if we have an input 0 in state 0, 0. We go to state 0, 1 and output a 0 because we're looking at this edge here. Okay. If we are in state 0, 1 and we input a 0, right? That means we are on this row. So we just cycle to the same state and we output a 0 again. Output 0, state 1. If we are in state 2 and we get a 0, we use this edge. Our output is 0 and output is 0 and our next state is 0, 1. If we are in state 3 and our input is 0, we take this edge here. So on this row for that edge, we output a 0 and our next state is 0, 1 again. What about for the ones? If we input a 1 in state 0, 0, we cycle to state 0, 0. 1, 0, 0. If we are in state 1 and we input a 1, we go to state 2. Oops, we should output a 0 here on state 0, input 1. So again, input is 0, 1, or input is 1 and current state is 0, 1. Then we go to state 1, 0. Output is 0. Next, input is 1 for state 2. Our next state is 3 or 1, 1, and our output is finally 1. Finally, it's 1. Then, if we input a 1 on state 3, we're looking at this transition. Our output is 0, and we go to state 0, 0. And we have our truth table. Let us develop the K-map, or K-maps, plural. So we're going to start with this column for O. We can say 0, 0, 0, 0, 0, 0, 1, 0. So our group is O equals I, A, B prime. I and A and B prime. Let's look at A plus. I, A, and B are our 3 input variables. Now we are going to look at this column for A, or A plus rather, going from the top, 0, 0, 0, 0, 0, 1, 1, 0. So A plus equals, if we group these, we have I and A prime B, or I and A and B prime. Let us simplify using Boolean algebra. Factor out the I using the distributive property. And then we can substitute for an XOR gate for A XOR B. Let's now look at the B plus input, or B plus output from the combinational logic. So we have input variable I, A, and B. A and B being the current state of the state machine. And we will now look at this final column, B plus. And we will just copy the binary digits from top to bottom. 1, 1, 1, 1, 0, 0, 1, 0. So we have one group and we have two groups. B plus equals I prime or A B prime. We have now our Boolean expressions. Why don't we try copying our Boolean expressions here over to a simulator and try simulating. So B plus equals I prime or A B prime, and A plus equals I A XOR B. Now, this is a very interesting thing that we can observe here. Look at O and look at B plus. We have a common term here between these two. If we wanted to, we could share the term. So let's try creating a new term. W equals A B prime. And then we can say O equals I ANDed with W, and B plus equals I prime or W. We'll set these as our four equations. W is just an intermediate variable that we are going to use. Let's bring this over to the simulator. And let's place it here. Now that we've placed our equations, we can place the flip-flops and draw the circuit. Simulation logic. Let's go and pull out a couple D flip-flops. 1, 2. We need to bring this just a little bit above the D flip-flops so that we can wire our output correctly. Okay, so that is our A prime signal. And now let us bring out our A signal here. We have B prime, B, A prime, and A. So A prime, B, B, and B prime. We now need to label I and I prime. Let us bring these input values now. So this will be I prime here. And let's place a simulation gate of an inverter. And this will allow us to develop I prime from I. So here is I and I prime. And because we have I prime for B plus, we have to have the inverter. For A prime, and B prime, those are developed automatically from the flip-flops that hold bits A and B for the current state. So we don't need extra inverters for those two bits. What is first? Well, we can place an XOR gate and an AND gate for A plus. Let's do that. XOR. And then we AND A. Let's take the A XOR exclusive OR of A and B. So A XOR B. And then we AND this with I. AND 2. We'll connect that to the flip-flop. So ANDing with I. There we go. Now we need A and B prime. So let's place an AND gate here. A and B prime. Now we need I ANDed with W for the output. Let's give ourselves a little bit of space. And Now we can connect one input to I, and we can connect this input to W here. So W, let's label W so we can keep track of it. W, oh, not Q, but let's call it W. So we know what the signal's name is. And we have our output. We AND W with I. And then we also need to OR W with I prime. Let's pull out an OR gate. And then OR W with I prime. Now, we need to connect our clock signal ourselves a little more space. We need to connect our clock signal to the clock input pins. And we need to start in state 0, 0. So our reset signal for the state machine connects to the reset pins of both the flip-flops, and the preset pins, or the set pins, S and S, of the flip-flops can be tied to the logic 1. So let's go to connectors and just connect it to a plus 5 volts. Plus 5 volts. We can now connect our input control switches and our output probes. Here's a clock and a reset signal, and our input and now let's connect our binary probe to our output pin. Now we are resetting the state machine right now because the reset pins are active low. So the state is being the state of the state machine is being reset right now. We need to set it to state 1, or set the reset pin to 1, and now we can clock the system. Let us take a look here with binary probes at the current state. This is just for taking a look inside. The state machine itself does not actually have these two pins as outputs, or this pin and this pin as outputs, but this is going to be very good for illustrating whether we're moving correctly from one state to the next. Let's try it out. So if we're inputting a 1 on the first state, let's take a look at our state diagram. If we input a 1 in state 0, 0, we're just going to cycle around to state 0, 0. And then if we input a 0, we're going to go to state 1. Let's try cycling in a circle and then going to the next state so we can test two edges. So our first one, we're going to cycle once. We stayed in state 0, 0. And now we're going to set the input to 0. We should go to state 0, 1. This should remain 0. And you can see after clocking, we went to state 0, 1. So far, so good. Let us consider the state diagram again. We are now in state 0, 1. If we input a 0, we cycle to state 0, 1, and we don't move. If we are in state 0, 1 and we take 1 as input, we go to state 1, 0. We can therefore test 2 more edges. So if we input a 0, we cycle. This is going to stay the same, 0, 1. Clock it. We stayed the same. Nothing changed. However, if we set this to 1, we're going to move to state 2. Let's see if that happens. Clocking 0 to 1 on the clock pin. And we are now in state 1, 0. Now, let's check the input here for 1, 0. If we input a 0 and clock the system, we should go to 0, 1. If we input a 1 and clock the system, we should go to 1, 1. But notice also that the output pin is no longer going to be equal to 0 in this case. It's going to be equal to 1 if the input is 1, or 0 if the input is 0. Let's try this out. Well, check the input and check this output pin. If we change the output pin, or change the input pin, clicking from 0 to 1, 0 to 1, the output pin changes immediately. Immediately. Is this expected behavior for a sequential state machine? Well, it seems counterintuitive, but because this is combinational logic and it is directly affected by the input pin, it is entirely conceivable that it will affect the output pin immediately. The key to understanding the state machine behavior is to understand that only when clock goes from 0 to 1 does the output mean anything. Otherwise, the output value or output values, depending on the state machine implementation, could be changing in the middle. They could be in the process of changing and are hence invalid until the system clocks from 0 to 1 on the clock input pin. So coming back, we are in state 1, 0. If we input a 0, we output a 0 and go to state 0, 1. So when clocking, we are looking at an output of 0. 1, 0, we should clock back and it should go to state 0, 1. We are in 0, 1 now. Changing the input pin doesn't have an effect because the output value is always the same for state 0, 1. But let's input a 1 and this will take us back to state 2. Boom. State 1, 0 or state 2. Remember that if we have an input of 0, then the output is 0. When we set this to an input of 1, then the output becomes 1. So when we clock our system from state 2 and an input of 1, we're going to see state 3 as shown here. State 2 goes to state 3 on an input of 1. It has an output of 1. We clock 0 to 1. We are now in state 3. Now, this is very odd because we went to state 3, but there is an output of 0. Well, we recognize 3 bits though. Why are we getting an output of 0? The key to remember is that we are looking only on the 0, 1 transition for the valid output value. Remember, on the previous clock cycle, we had an output of 1 here. So when we clock on state 3, it is going to be an output of 0 regardless. Checking the edges here and here, the output value for both edges from 3 going to the next state both output values are 0. So it is expected behavior. We'll take an input of 0. This should take us to state 1. Clock, and we go to state 1. So we have checked almost all the edges. 1, 2 edges from state 0, 1, 2 edges from state 1, 1, 2 edges from state 2, and just this one edge from state 3. We need to check this second edge from state 3 as well, and then we've covered all 8 edges. We've only checked 7 of the 8 edges so far. Let's try it. Let's bring ourselves to state 3 by clocking a 1. We're in state 2, and then clocking again. We are now in state 3. So if we take an input of 1 here, it should take us to state 0. Input of 1, this state goes from 1, 1 to state 0. And we have confirmed all the edges of our state machine.